Welcome to this lesson on iterative methods for root finding. This is the second part of this topic where we move on from the bisection method and introduce some other methods. But I think it's good for us to start by reviewing the rubric that we use for talking about how good a particular solution method is. So things we care about are, does the algorithm actually converge to a root? If so, how fast does it converge? And this next issue is one that you'll get into a little bit coming down the road, but it's how stable is the solution process to tiny numerical errors. This has to do with how numbers are stored on computers, which is a very important topic that you will learn more about. But of course, whatever the ideal method is might change depending on context. So oftentimes there's a trade-off between the speed of convergence and robustness, meaning the algorithms where you can guarantee convergence tend to be slower. And then of course you'll find yourself in different situations where you have different information available about the problem, and that might inform your choice of algorithm. Do you have a bracket available for the root? Do you have some a priori information about the function, right? Like how smooth it is, if it belongs to a particular class of functions, if it just has a single root. And then also it matters if you're just interested in a single root or in multiple roots. To review what you know about the bisection method, if you start with a bracketing interval that has a root inside, you'll always converge using bisection, and the error cuts approximately in half each iteration of the algorithm. What the cons are is that you really ignore a lot of information, right? You're only using the sign of the function values at the endpoints of your bracketing interval. You're not using the magnitudes of those function values, like are they close to 0 or far from 0. You're not using any other properties of the function. And also, this method will definitely only find one root, right? So if you choose a bracketing interval with several roots inside, the bisection method will only converge to one of them. Convergence of the bisection method is pretty slow, so it's linear, or in the notation we've been using, q equals 1. We can introduce Newton's method, and we'll just draw a picture of how this works. You start with an initial guess x naught, that's right here. You go up to that point on the function, you calculate the derivative of the function, and you use it to construct this tangent line that you see drawn. You find where that tangent line intersects the horizontal axis, and that is your next estimate for the root. And then you can repeat the process, right? So you'd take x1 here, you'd go up to the function, you'd draw a point, you'd calculate the derivative, draw the tangent line, see where it intersects the horizontal axis, and that would be the next root. If all goes well, if Newton's method converges, and if the root it's converging to is a simple root of the function, then it turns out you get quadratic convergence. And I should say, that's huge, right? Quadratic convergence is way, way, way faster than linear convergence, so that's a nice property. But of course, Newton's method is certainly not guaranteed to converge. There's lots of things that can go wrong. Here's a kind of fun example of when something goes wrong. Here you have a function, kind of looks like a quartic, and we can pick this initial guess, x naught. You go down to the function here, and you draw a tangent line, find where it intersects 0, that gives you x1 here. You go down to the function, you draw the tangent line, find where it intersects 0, and you get back to x naught. So Newton's method will just flip between these two values, x naught and x1, and never converge to any root. That's just one example of the sort of thing that can go wrong. The secant method is very similar in spirit to Newton's method, except you don't have to calculate a derivative, right? So Newton's method depended on us being able to specify what f prime of x is at every guess x sub I, and secant method doesn't require that. So rather than drawing a tangent line, what you do is you used past guesses, past iterates, to construct a secant line. So here's how this works. You actually have to start the secant method with two guesses. So we're going to seed it with the guess x naught and x1. No derivatives necessary. You just take those 2 points and you look where they fall on the function, and you draw the line that connects them. That's the dotted line shown here. That's called a secant line. You find where the secant line crosses the horizontal axis. That's here at x2. That's your next approximation for the root. And then you'd repeat, right? So instead of using x0 and x1, you'd use x1 and x2. So that would be this point up here and this point down here, and you draw the secant line that connects them, and that would give you this point, x3, and so on. And it turns out that when this converges, it's doing so in a superlinear manner. So it's something between linear and quadratic. It turns out you can prove you get Q around 1.62. Then there's something called the IQI method. IQI stands for inverse quadratic interpolation. And what that means is that instead of drawing a tangent line and instead of drawing a secant line, you draw a sideways parabola, right? So not a parabola of the form y equals g of x, but one of the form x equals g of y, where g is quadratic. So it's a sideways parabola. You need 3 points to determine a parabola, so you have to seed this algorithm with 3 guesses. So you start with x0, x1, and x2. You look where those points fall on the function, that's here, here, and here. You draw a parabola that passes through all of them, that's this curve, I circled the start of it here, this dotted curve. You find where that sideways parabola passes through 0, it's here at x3, and then you would repeat this. Instead of using x0, x1, x2, you'd use x1, x2, and x3 and draw another sideways parabola. And if this algorithm converges, it's also superlinear, a little bit faster than the secant method. You get Q around 1.84. Now we're going to introduce Brent's method. This is a hybrid method that tries to combine some of the best aspects of bracketing methods with some of the best aspects of faster methods. So here's very roughly how it works. You start with a bracketing interval, right? So you start with some AB where you think there's a root inside, and you do the following. First, you try to take one step of inverse quadratic interpolation, okay? And then you check. If you were to accept that next guess using IQI, would it result in your bracketing interval being cut at least in half? And would it result in your root giving you a function value that's closer to 0 than it was before? If both of those things are true, then you accept that as your next guess. If both of those things are not true, then you reject using the IQI method, and instead you try a step of the secant method, right? So you would do a secant method step. You would check, does that cut my bracketing interval in half, and does my guess for the root get closer to 0? And if it does, you would then accept that as your next guess for the root. But if it didn't, then you would just go ahead and use the bisection method. And after you accepted a step of the bisection method, you'd repeat, right? So you'd go back up to step 1 here and first try IQI. If you reject that, you'd use secant method, and if you reject that, you'd use bisection again. And it turns out that this method is what's used in the built-in command uniroot in R, so that's something you can check out if you're interested. All right, thanks for listening.